So let's start discussing PN junction in this lecture. Before that, let's just go through some basics. Let's take a semiconductor and dope it with an atom which has 3 electrons in outer shell. Silicon has 4, so this dopant atom has 3. So it is actually one shot to form the covalent bond. This type of semiconductor is a p-type semiconductor. Boron is an example. If you dope the same semiconductor with a piece of silicon with a dopant atom which has 5 electrons, 4 can form covalent bond to this neighboring silicon and 1 is free to conduct current. This type is called an n-type semiconductor. The majority carriers in a p-type semiconductor is holes and n-type it's electrons. Minority carriers is electrons here in a p-type semiconductor, and in a n-type semiconductor it is holes. Minority character is not 0 given by Moore's law. We just seen before that it is not 0. Both are still electrically neutral. Can you discuss the reason why so? Even though there are free electrons and free holes here, the material is still electrically neutral. Now during this course of PN junction, bipolar and MOS transistors, we'll have 6 entities to deal with. We'll just take a look each one of them so that it's a little bit easier to see the diagrams later. Okay. So we'll talk about the particle, what is the symbol we use, what is the charge, and there is a reason for the charge. Electron will be represented by E minus. It has a negative charge. Hole will be represented by a H plus and it has a positive charge. This is relatively straightforward. Acceptor atoms like a boron will be represented by this kind of yellowish circle, and it is electrically neutral because the number of electrons equal to number of protons. Donor atom like a phosphorus will be represented by a blue circle. This is also neutral, and it's neutral as we just said before because number of electrons equal to number of protons. This is 5 in the outer shell, this is 3 in the outer shell electrons, but the total number of electrons is equal to total number of protons in the nucleus. The same way here, total number of electrons in all the shells is equal to total number of protons in the nucleus. So they are electrically neutral. Now, an acceptor atom which has accepted an electron will be represented by this orange circle but with a negative sign because an electron has come and occupied the outer shell. This is negatively charged. It's an acceptor atom which has accepted an electron. So the number of electrons is more than the number of protons in the atom. Hence it is negatively charged. Electrons is 1 more than the protons. Same way, a donor atom which has donated an electron will be positively charged. So we'll put a positive here. It will be positively charged because number of protons is more than one number of electrons. Okay? One electron has gone away somewhere. So one electron is reduced, but the proton is the same. So protons is 1 more than the electrons. Okay. Now let's talk about a PN junction. Let's take a semiconductor which is doped by acceptor atom. These are acceptor atoms, right? And another piece of semiconductor which is doped by donor atoms, okay? And we form a junction. Okay? A junction is formed here. What happens? Ideally, this is not formed as shown in the animation, but for our understanding, this is a good starting point. Okay? So what happens? You can see there are more number of acceptor atoms here. There are more number of donor atoms here, which means there are more free electrons here. There are more holes here. Okay? So this is the p-type semiconductor and this is the n-type semiconductor. Right? So in the p-type semiconductor, we know the number of holes is more than the number of free electrons. So holes is somewhere here. Moore's law will give you what the number of free holes is, free electrons is. Same way. So the number of free holes, which we'll call it P subscript P, is nothing but approximately the Na, right? The doping concentration of the dopant, right? And Np will represent the number of free electrons, N for electrons, in the p-type semiconductor. The subscript tells me what type of semiconductor it started with. So NP is number of free electrons in the p-type semiconductor. PP is number of holes in the p-type semiconductor. Right? And PP is Na, and you can calculate NP by mass law. Same way, number of electrons here will be represented in the n-type is represented by number of electrons is n in the n-type semiconductor subscript n, and the hole is represented by P in the n-type semiconductors of P of n, P subscript n. Okay. And n of n you know is Nd, because that is the doping concentration here. Okay. So when they are merged, this is what happens. Right? This is how the concentration looks like. So you can see the number of holes here is much larger than the number of holes on this side. The number of free electrons here is much larger than the number of free electrons this side. So what will happen? Right? Yes, you're right. You would expect some amount of diffusion to happen, because there's a concentration gradient of electrons here this side, concentration gradient of holes this side. Right? So concentration gradient is formed. So when a concentration gradient is formed, some amount of electrons from here will flow to the other side, and some amount of holes will go to the other side. Right? So you will get a gradient, concentration gradient across distance like this. Okay? Far away nothing will happen, but closer to the junction where it was, you will see that the holes starting to reduce and go to the other side till it becomes same in the bulk of the n-type. Same way for the electrons. Right? This is exactly what I had asked you to discuss. Will it become flat at some point like this? Okay. Number of holes across the entire semiconductor, will it become like this, flat? Number of electrons on the other end will become flat like this? Probably not. We'll just take a look at that. Right? So electrons from donor side diffuse to the acceptor side and occupy the holes negatively, creating a negatively charged atom. Right? So electron from the donor side diffuse into the acceptor side, occupying some holes. And once we know an acceptor atom accepts an electron, it becomes negatively charged because it has got one electron more. Right? Since some electron diffused from the n side is positively charged because one electron has moved away from here. Okay, so just take a look at it. This is a p-type semiconductor. This is the n-type semiconductor. Right? An electron from the n-type semiconductor, which is here, right, because of diffusion forms a current and goes to the other side. Right? When it does that, it exposes, though I've shown only one electron, assume there's a bunch of electrons here. Right? It exposes a set of positively charged atoms here because the electrons are moved away from this atom to this side. And what happens on the other side? Since these electrons occupy a hole, they become negatively charged atoms here. These atoms can't move now. They are all fixed atoms, right? But they are positively charged and negatively charged. Right? So when you have a positive charge to a negative charge, you get an electric field. We've seen that before. This is basic physics. If you have a positive charge on one side and a negative charge, an electric field starts from the positive charge towards the direction of the negative charge. Okay. Because of this electric field, you should get a drift current because there are free charge particles, electrons and holes, and an electric field is set up. And we know a drift current sets up when there is an electric field. Right? So now we are seeing what we learned in the last chapter coming into play here. There's a diffusion current because of the concentration gradient, and there's a drift current because of a resultant electric field that gets set up. Right? Initially, the diffusion current is much larger than the drift current because the electric field is small. The concentration gradient is much larger than the current that is set by the drift current. The drift current actually will oppose the diffusion current. If it didn't, then everything will just move over to one side, right? So drift current is like the friction that we talked about in a mechanical system, in the sand example. So drift current opposes the diffusion current. Now, these atoms, which are negative and positively charged, are actually immobile because they're atoms. They're fixed into the lattice, but they're charged. They can't move. So they don't contribute to any conduction. They're charged, but they can't contribute to any conduction because they can't move. Right? Only if a charged particle moves, we have current. These extremities away from the junction, they're still charge neutral because n-type or the base silicon was charge neutral. Right? So at far away from the junction, the material is still charge neutral. but near the junction there's a region of charged immobile ions. Okay. So what happens now? Diffusion current is still larger than drift current, so some more electrons will try to go from the N type to the P type, right? And what it will do? It will expose some more positively charged ions here, and correspondingly some negatively charged ions will be formed here. What will this do? This will increase the electric field, right? Because there are more number of charged particles. There are positively charged particles here, more number of negatively charged particles. The strength of the E field will increase. So will the amount of distance these ions occupy. Right? So the diffusion current still is larger than the drift current, but not by a large, because the drift current is actually increasing. Diffusion current is reducing because the concentration gradient kind of reduced a little bit. Okay? Because some electrons have already gone this side. Okay? But still the diffusion current is larger, so some more electrons went from this side to that side. Some more ions got formed, positively charged ions got formed here, some more negatively charged ions got formed here, till such a time that the electric field increases so much, right, that the drift current becomes equal to the diffusion current. Right? That's bound to happen sometime, because the electric field keeps on increasing, causing a drift current to increase. A diffusion current was reducing. At some point they'll become equal, and once they become equal, there'll be no effective movement of charges across, because the diffusion causes a movement of charge, drift causes an equal amount of charge to go back, right? So under this condition, we know diffusion current is given by Q dn by dx. Remember, this is the diffusion current because it depends on the concentration gradient, and the constant proportionality was diffusion constant of the electron. In this case, I was writing for the electron. You can write it for the holes as well, right? Qn, mu, and E, and this is the diffusion drift current, Qn, mu, and E. Right? Remember, this was the velocity Qnv, which was replaced by mu n times E. Same way for the hole, Q dp by dx equal to Q p mu p ex. Right? So the electric field has to satisfy. It will satisfy both these conditions, that the electron current and the hole current both become effectively zero. Right? That means the diffusion current for the electron is same as the drift current for the electron, and the diffusion current for the hole is same as the drift current for the holes. Okay. Now you can see a field getting formed here. Right? In the sand example, this was the frictional force. Right? So not all charge go from or not all electrons go from the N type to P type. It goes till such a time such that a sufficiently large electric field is formed, which opposes the motion of electron. That's it, right? So it will find an equilibrium at this point. Right? This presence of an electric field across a distance means you have a potential drop. Right? So you have a potential drop across this junction. Right? Because potential is nothing but integral of E dot dx. Right? So since E is across some distance, you'll have a potential drop from here to here. We'll just calculate that next. Right? So we just had this, where the charges, these are the immobile positive charges, and this is the immobile negative ions here. Right? This region is called the depletion region. It's called depletion because there are no free charges here. There are charges, but they are not free to conduct current. They are not free to conduct current because these immobile charges are actually atoms which are charged positively or atoms which are charged negatively. Right? Current is carried only by free electrons or free holes, and that is absent in this region. Since this region is depleted of free carriers, it's called the depletion region. Right? It's depleted of free charges. Right? The distance from the junction into the p-type semiconductor, let's denote by xp, right? And the distance of the depletion region from the junction into the n-type, we'll call it xn. Right? This is an approximation where this is called an abrupt junction approximation, where the junction was pretty abrupt, but let's keep it so. Right? It makes our calculation much more easier. xp, xn. xp is the distance of the depletion region from the junction into the p-type, and xn is the distance of the depletion region or from the junction in the n-type. So what do you expect? From charge balance, you know that the number of immobile positive negative ions should be the same as the number of immobile positive ions, because the entire material is charge neutral, right? To start with, they were charge neutral. So this charge has to be same as this charge. Even now the entire material is charge neutral, it's just that internally it got distributed, right? What is the charge on this side? It is Na. Na is the number of dopant atoms per unit volume, right? Let A be the cross section area, xp is the depth or the depletion region width, right? So xp into A is the volume of the depletion region in the p-type material, and since there are Na atoms per unit volume here, it is Na xp into A. Similarly, on the other side will be Nd xn into A, where xn into A is the volume of this region, right? Because I have not shown you the cross section, but we take assume the cross sectional area as A, like this, right? Then that volume is xn into A, in which Nd dopant atoms are there. So Nd xna, right? So A will cancel, and you will get Na xp equal to Nd xn. Very simple, straightforward relationship. Na into xp equal to Nd into xn. You can clearly see depletion widths are inversely proportional to their doping density. So if you increase the doping density, xp will reduce. If you increase doping density on the n type, xn will reduce. Right? Now if you plot the electric field, right, assuming this is the positive x direction, right, plot the electric field in the x direction, right, you would expect the electric field to be negative, because electric field is pointing in the negative x direction. It's just a convention. Negative, electric field is from the positive ions to the negative ions. So it is in the negative x direction, right? So if I plot E along x, positive x, right, you're going to expect the electric field to be negative, right? Electric field in this region is going to be 0, right? Because there is no potential drop here, there are no charge particles here, basically. Fundamentally, because there are no charge particles here. Okay? The first time you encounter a charge particle is at the boundary of the depletion region, and it keeps increasing here, right? The amount of charge particle keeps increasing till you get to the boundary, the junction, right? So if the amount of charge particle keeps increasing, the electric field actually keeps increasing, right? But increasing in magnitude, and since it's pointing in this direction, it will be increasing in magnitude but negative in sign. That's what will happen here till it comes to the junction. Okay, it increases linearly. We're going to assume linearly because we assume the doping to be uniform. In reality, there is a shape to it, but it doesn't matter for us. It's a good, fairly good enough approximation. Okay. Now, what happens as we go into this region from here now? There will be some positive charges which are encountered now, which means the total amount of charge, right, inclusive of this, starts to reduce now. If the charge starts to reduce, the electric field tends to reduce, right? And it will become 0 back here, because the number of charges of the positive equal to number of charges of negative. So the net charge in this space will be 0. So it has to come back to 0 at this point. And since there is no more free charge particles here, the electric field there will be 0 as well. Right? You understood now? So the electric field is a function of amount of charge that is there, and since it is pointing from the, in this case, right to left, and we are calling the positive x-axis from left to right, it is negative. Right? So it goes down like this and comes up like this. It is maximum at the junction, because that's where the maximum charge is encompassed. Actually, this is a simple application of Gauss law. We'll discuss that later if you have time, but let's just assume it is Gauss law, a simple application of Gauss law, and that states that the electric field is proportional to the charge enclosed, and that statement alone will tell you that this is going to be like this. Okay. Voltage, on the other hand, is nothing but, so we said that since the electric field is going from here to here, this has to be at a higher potential than this. Right? Voltage is nothing but integral of E dot dx with a negative sign. And if you do that, right, there will be no voltage drop here because electric field was 0 here. Electric field was 0 here. Then it starts to increase because of this minus sign. The area under this curve, basically, after this will keep increasing, right? And then when it reaches here, there are no more integral. The area contributed by this part is 0, so it saturates. So there's a voltage drop across the junction, which is this, right? And this voltage drop is denoted by the symbol Vd, which is it's called the built-in potential. Okay, so that's what we'll take a look at. We'll just calculate the built-in potential. I drift is equal to I diffusion is when the depletion region stops expanding. We've seen that, right? So we'll just take it very simply, equate it. Qp mu p E equal to E of x, but I'm just writing E right now, equal to Q dp by dx. Right? And I'm writing it for hole. You can also write it for electron, we'll come to the same conclusion. Right? And E, you know, is nothing but minus dV by dx, because V was the integral of E dot dx with a negative sign. So electric field definition is minus dV by dx. So if you just substitute it here and then rearrange the terms, Q and Q will cancel, right? dV by dx, this dx will go. So dV is minus dP by mu p, dP by p. Right? This dP by mu p is actually kT by q, right? But we'll come to that. That's an Einstein's equation. Right? So if you integrate both sides, right, you get V1 minus V2 equal to dP by mu p ln Na to Pn. You can do that by yourself, where Na comes because it is P subscript P, the amount of holes in the P side. This is a simple integral because the integral of 1 by P is ln of P, and if you substitute these values, you'll get this. Right? And Pn, we know, is the number of holes in the N side, and that is given by Ni square by Nd. So Nd goes to the numerator, so it becomes Na Nd by Ni square. Right? So dP by mu p ln Na Nd by Ni square. Right? dP by mu p is actually nothing but kT by q, where k is the Boltzmann's constant, T is the temperature in Kelvin, and q is the charge of the particle, electron charge. So kT by q ln Na Nd by Ni square. This is the voltage difference across the depletion region. Right? This kT by q is actually represented by Vt. So it's Vt ln Na Nd by Ni square. Right? This Vt is approximately 26 millivolts at 300 degree Kelvin. This is just the Vt. Right? The built-in potential depends on Vt and the doping concentration. Right? This is the built-in potential. This is called the built-in potential and depends on the doping concentrations as well. Right? But you can see that the doping concentration is at a logarithmic scale. So it is sensitive but not ultra sensitive. Right? So I've given you a problem later for you to work out what happens if these things are changed by orders of magnitude, and you'll see that the built-in potential doesn't dramatically change. It's a good thing to just do an exercise and be comfortable with it. So the built-in potential is given by Vt ln Na Nd by Ni square. Remember, this is a function of temperature because Vt is a function of temperature, Ni is a function of temperature. Okay. So we've calculated the voltage, right? But we still need to know of what is the electric field, what is the total charge, what is the width, everything. Right? To calculate that, we'll start with the Poisson equation, which states that dE by dx, the rate of change of the electric field, right, is rho by epsilon naught, where rho is the charge density. This is another manifestation of Gauss law, but let's just keep it at that. dE by dx equal to rho by epsilon naught, where rho is the charge density, charge per unit volume basically. Okay. So in the N side, in the depletion region, since we said the depletion region extends to xp in the negative side, minus xp less than x which is less than 0, the rho density of the charges in the depletion region is minus q times Na. Then we've seen that because on the p side the charges are negative, because they accepted an electron, and Na is the density there, right? Na was the doping density, so it minus q times Na. And on the positives, on the other side of the depletion the junction, in the depletion region, the charge density is q times Nd, positive because it has lost an electron. We've seen that, where x lies between 0 and xn, right? Because this xn and xp are the limits of the depletion region. Beyond that, anyway, rho is 0, right? Below this xp it was 0, above this xn it is 0, because that's charge neutral. Right? Charges exist only in the depletion region. They are immobile, but they are charged particles. Right? Now, integrating both sides and equating the fields at x equal to 0, right? Because there's a field that goes from, we've seen that a field starts from the depletion region, goes through the junction, goes to the other side. Right? At the junction, both of these should give me the same electric field, right? Because they cannot be, because electric field is just one. Even though the depletion regions are split into two halves, the electric field has to be the same at x equal to 0, which is the junction point. Okay? You'll just integrate, because you're going to integrate, because this is E is nothing but integral of rho by epsilon dx, right? And you're just substituting the rho for both these equations, because the rho is not same in these two regions. I'm just substituting back here, right? Minus q, this is the rho on the p side by epsilon dx, and this is the rho on the n side by epsilon dx, right? And it's just a very simple straightforward integral, right? It is just x plus c1, and this times x plus c2, right? And the regions are appropriately marked. We know that at x equal to 0 now, right? The electric field has to be the same, which what it tells you is c1 equal to c2, right? At x equal to, that is 1. It's also that at e equal to x minus xp, the field is 0, right? That is the other end of the junction of the depletion bit, right? At x equal to xp, or even less than that xp, it is 0. So we'll take the boundary condition x equal to minus xp, the field is 0, which implies that minus q na by epsilon into xp, right, plus c1 equal to 0. So c1 is this much, right? You can substitute and check yourself. Same way, at xn also it is 0, so you can calculate c2 with this, right? C2 is minus q and d epsilon xn. You can just substitute in this equations, you'll get it. Not a big magic out here, right? We also know that electric field at x equal to 0 is same. It's not 0, but it is the same. Both equations should give me the same value, right? So if I put x equal to 0, these terms vanish. C1 has to be same as C2. Is C1 equal to C2? Qna by epsilon xp is equal to Qnd by epsilon xn, right? So q by epsilon will cancel. We'll end up with naxp equal to ndxn, and we have seen this already from charge neutrality, right? So no surprise. Looks like our equations are right. Okay. So now let's calculate the voltage. We got a expression form for the electric field. I saw that it was actually linear as well. I forgot to mention that, but it was a linear function of x, as we had drawn before. Now let's try calculating the voltage. Voltage is nothing but integral of E dot dx with a negative sign, right? So we've seen that the voltage increases like this from the graph, right? We'll just have to calculate what the voltage is. We actually have calculated the voltage as well, right? This is the built-in potential. It was Vt ln Na by Na square. But there's a reason for doing it, so that we get an expression for Ex as well. We'll see that, right? So when you put the Vx, right, again since there are two regions, minus xp to x to 0, right? The charge densities at the E field is different. The equation for the E was different, right? So just substituting it for that here, and that evaluation of that tells me that it is Qna by epsilon x square by 2 plus xp x, right? So I'm just putting that x out, x by 2 plus xp times x plus c1. Same way on the negative side, on the n side, you substitute back the electric field there and evaluate, you'll get this. So very simple integral, just substituting what we have calculated for Ex to calculate the voltage. Okay. Now, assuming that the voltage is always a reference, right? It doesn't matter what it is. With respect to a potential point, we can say the voltage of another point, right? Assuming that V at minus xp to be 0, we can assume that, right? Because voltage is just a difference that we talk about. And the potential is the same at the interface in the above equation. These two equations tell me, this equation tells me this curve, and this equation tells me this portion of the curve, right? So both these equations at x equal to 0 should give me the same voltage value as well, just like for the electric thing that we saw. Okay. So V of x, well then if you substitute and go calculate C1 and C2 and substitute, you will get QNA by 2 epsilon x plus xp square for in this region, right? And this term for the like on this side, right? I'm just using this V at x equal to minus xp equal to 0, and the fact that the potential is same at the interface in the above equation to do this, right? Here actually it's very easy because at this point, if I substitute x equal to 0, both these terms go to 0. All it says is C1 equal to C2, right? And then I'll put x equal to minus xp, voltage is 0, so I have to put it here. I can calculate C1, and once I calculate C1, I know C2. So I know C1 and C2. I just substitute back in these equations to get this forms. Okay, so relatively straightforward equations to solve. The more important thing is to understand what is happening, what the equations tell us. Okay. So potential at x equal to xn should be Vd. We have known that, right, before. So we'll calculate at xp, we assume 0. We'll calculate what happens at xn. Okay. So xn, if you substitute in the second equation in the previous point, you'll get this. Vo equal to q by 2 epsilon naught nd xn square plus naxp square. It's just a straightforward substitution of x equal to xn in the second part of the equation, right? And we know naxp equal to ndxn. This is charge neutrality, right? So if you substitute that, I'm just rewriting this form into this, right? I'm just eliminating xp from this equation because I have to calculate xn and xp's now, right? Because we know Vo, this is the built-in potential, and we already calculated that. The only unknowns here are xn and xp. I know a relation between xn and xp, so I write xp in terms of xn here, so I can calculate xn and then hence calculate xp, right? So do that, you'll get this, and just rewriting nd as nd square by nd, so that the form looks similar here for both of them. Right? So xn now is very easy to calculate, is 2 epsilon v naught by q na by nd na plus nd. You just substitute this. Xn is a simple x square relationship here. You just substitute, you'll get this. From this, xp also can be calculated by substituting back in this equation, right? You will get this form, right? And we know xn plus xp is the total bit W of the depletion region, right? So when you do this, you'll get this form. You just have to work a little bit around to get it to this form. But you can prove it yourself. Take it as an homework exercise just to do this. Okay. So you get a W, which is this. Then now this is an interesting thing, right? So you can see W depends on VO, NA and ND. Of course, epsilon and Q depends on the material, and Q is fixed. Epsilon depends on the material, right? Now VO depends on the doping as well. But VO we saw was a weak function of the doping because it is ln NaND by Na square. So ln actually desensitizes it a lot amount, right? But NaND comes here, right? So you can see larger doping means lower W. This is important, right? Larger doping means this factors will become smaller and smaller, hence the width will reduce. So larger doping, smaller W. The depletion width actually reduces with larger doping. Okay. And individually, once you calculate W, because this is a nicer, easier form to remember, Xn is W times Na by Nd by Na, and Xp is W times Nd by Na plus Nd. You can see that the inverse relationships here, right? Back. Xn depends on, let's say the sum is fixed, right? Xn depends on Na, Xp depends on Nd. The other side is doping. So if there is more doping on the Nd side, Xp will increase. Because all it's saying is I have more electrons per unit volume than there were number of holes. So even if a small unit volume of electrons go into the number of holes, it has to expose a larger region to get so many acceptor atoms. Think about it that way, right? So larger concentration means it will penetrate more deeper onto the other side. Very logical. Okay? Lightly doped region has more width. Okay? So if ND is more, XP is larger. If NA is more, XN is larger. Right? Other way of saying it, NA is less, right? XN is lesser, or XP is larger. Lightly doped region has more width. Right? Overall width will reduce if the doping increases. And the relative portion of XN and XP depends on the relative doping densities. Now, so we got the width, we know XN, XP, we know VO. Now let's take up the electric field. Okay. So E again in the two regions, you can go substitute back, you'll get this as E's. Okay, we're just reiterating this back again. And at E at X equal to 0, if I substitute here, this minus QNA XP by epsilon. Okay. You can do it here as well, but I've just taken one. They're the same. Because NDXN is equal to NAXP. And we know that the shape of the E was like this. So we need to find, and we know that at the junction, the electric field is the maximum, right? And this is the value here, right? So E equal to X equal to 0 is nothing but E max, and that is this. So we'll just substitute for XP, and we'll get E max as this. Right? Now look at the thing here, right? Larger doping means, let's say if Na and Nd are increased, 1 by Na and 1 by Nd will reduce. Since they are in the denominator, this entire factor will increase, right? So E max actually increases with more doping. So you dope more, the width is reduced, but the field is increased, right? With depletion region, width will reduce if both the dopings have increased, but the electric field will increase. Okay. Now all that's remaining is the charge on each side. Charge on each side is nothing but QND XN or QNA XP, right? Because that's the charge on each side. You substitute back, you get this. Because once you know XN, XP, you can do whatever you want. Right? More doping density, more charge expected. Right? Larger doping, larger charge expected, right? Nothing surprising about it. Right? Right? So larger the doping, lesser the width, larger the doping, larger the field, larger the doping, larger the charge. Okay? Now, this is a problem for you to work out. Assume a silicon PN junction doped with Na and Nd, which are given here at 300 Kelvin. Find the built-in potential. Straightforward thing. Right? You can just substitute, you know the value of Ni, just substitute back and get this. Okay. Now, what happens if Na is increased 10 times? What is the difference in from the original VO? How much does the VO increase by? Right? What happens if Na is decreased 10 times? What is the built-in potential? How much does the built-in potential change? This problem is given such that even though Na is increased or decreased 10 times, I want you to understand how much the built-in potential is sensitive to the Na. Right? Because it's inside lawn, you would expect it not to change 10 times. It should be much lower than that. You'll see that when you do the problem. Okay. So far we have seen a PN junction formed by joining two materials which are P doped and N doped. And when you did that, we had a depletion region formed with the positive ions here and negative ions here. This is the depletion region, and these are immovable carriers. Because of the distribution of positive and negative ions, there's a field from the N side to the P side. Consequently, there was an inbuilt potential with the N side being higher than the P side. We've seen that so far. We also calculated the widths of the depletion region, assuming doping concentration, etc. Right? Now, we saw that the total charge that the depletion region carried was given by this formula, okay, where VO was the inbuilt potential. Now, let's say external reverse bias is applied. We call it reverse bias because the N is taken higher than the P side by a value VR. Already there's a built-in potential VO. Now I'm applying additional potential VR on this side. What this additional VR will do is will strip off some more electron from this side and get them to this side. Okay? Like this. More electrons will go from the N side to the P side. because electrons will get attracted to the positive side. The battery will then push it onto this side, and here current can't flow. Right? So in effect, the depletion width will increase because electrons are gone from here to from one side to the other side. So number of positive ions here will increase because electrons are gone from here, and the number of negative ions here will increase because electrons go and occupy an acceptor atom, and the depletion width as a consequence increases. It is also true that because of the depletion width is increased, more charge is stored. Though the entire material is still neutral, the charge here is increased. The charge here is also increased by the same amount, but to the positive side. Because the charge has now changed, and it's a function of the voltage that we apply, okay, you can call that there is a capacitance. Okay. So new charge in the depletion region is given by the same thing, except the VO is replaced by VO plus VR, because that's the additional potential that we applied across the junction. As charge changes as a function of voltage, this is the total charge, is changing as a function of the voltage applied, there must be capacitance. Capacitance is nothing but dq by dr, dq by dv, right? The change in charge to the change in potential applied is the capacitance. Okay. So in this case, it's dqr by dvr, which then can be calculated to be this. Okay. So we have a capacitance which is inversely proportional to the voltage applied. That means larger the voltage, lower the capacitance. But larger the doping densities, larger the capacitance. Because larger the doping densities, more charge are uncovered. It is inversely proportional to the square root of the applied voltage. This also can be normalized and written as CJO divided by square root of 1 plus VR by V naught, where CJO is the capacitance and VR equal to 0. That means when no external voltage is applied. Even then there's a capacitance. Okay. So you can see as you increase VR, the capacitance will reduce. Okay. So I hope this one is clear that as you apply external voltage, more charges are uncovered, which then means there is a capacitance. The charge increases as the square root of V, external voltage applied, hence the capacitance decreases with the square root of V. If charge increase proportional to VR, then the capacitance would have been a constant. But since it's not proportional to VR, but it's at a rate lower than VR, dq by dVr is given by this. Okay? The capacitance actually decreases with the increased potential that you apply. Okay. Let's do a problem now. Okay? Let's assume there is a silicon PN junction doped with an acceptor atom 2 into 10 power 16 per centimeter cube, and ND is 4 into 10 power 16 per centimeter cube. It's a PN junction. Assume that the silicon permittivity is 11.7 into 8.85 to 10 minus 14 femtofarad per centimeter. Farad per centimeter. This 11.7 is the specific permittivity of silicon. This is the permittivity of free air. 8.85 to 10 minus 14 farads per centimeter is the permittivity of free air. So this is the effective silicon permittivity. And Ni you know is already 1.5 to 10 power 10 centimeter per centimeter cube. This tells you it's at 300 degree Kelvin. Right? All we have to do is calculate the capacitance at zero bias when no external bias is applied. Then calculate the capacitance at the reverse bias of 0.5, 1 and 1.5. It's a straightforward application of the previous formula. Just take a look at it. Only thing I would like you to do is express the answer in femtofarad plus per micron square. Okay. The reason for doing this is the capacitance will be of this order. Okay. It will be a fairly small capacitance, femtofarad per micron squares. Okay. Here remember it's farad per centimeter, this is centimeter cube. So just remember the units when you convert it. Okay. What happens to the zero bias capacitance when ND is increased to 4 into 10 power 17? What do you think should happen? Should it increase? Should it decrease? Right? More doping means more charges. More charges means more capacitance. Right? So you should expect that the capacitance will increase. Just take a look at the numbers and see what it tells you. So we've seen the capacitance, we've seen how the depletion widths are formed, we've seen how the electric field behaves with the function of the doping. Okay. Let's just talk about one other atom, which is junction breakdown. What happens when the reverse voltage is further increased? We applied a VR, we calculate the capacitance. Can I keep increasing VR? Will the material behave the same way? let's take a look at it. Right? When I increase the VR, the E field at the junction increases. Right? Now at silicon, at typically about 1 volt per micron, free electrons will have sufficient energy to knock out electrons from the atoms. Right? That means they gain sufficient energy. This new electron will also accelerate and knock off more electrons. Okay? This leads to a multiplicative breaking of bonds and more free carriers are produced. This is called the avalanche breakdown. Right? In a heavily doped PN junction, on the other hand, the field increases dramatically because we know that the field is a function of doping. Right? So if you have doped it heavily, the field increases very dramatically. This field pulls the electron from the valence band to the conduction band, causing a huge change in current. Here it was electrons knocking off other electrons. Here, just because of the field, right, the electrons are pulled. And this is called a Zener breakdown. Okay. So this is what you're talking about, silicon with a reverse bias. As you increase the reverse bias, electrons go and knock out more electrons out here. And this more electrons will knock out even more electrons. This is your avalanche breakdown. Okay. So just looking at the reverse thing, right? So this is your avalanche breakdown. Avalanche breakdown happens when the doping densities are not very large. But if the doping densities are large, you know that the internal electric field actually is already high. On top of it, you give it a little bit more push, you'll have a Zener breakdown. This is for a heavily doped semiconductor piece of PN junction. Okay, so these breakdowns are actually important to know because you don't want to stress the material beyond this, because now it becomes uncontrolled current, right? Very large current, and typically this causes to thermal failures in the device. Sometimes we use Zener breakdown as a reference voltage. We'll see that maybe in the design class somewhere. This can be used, but if it is a controlled breakdown, it is good. Right? But if it's an uncontrolled breakdown where the current actually dramatically increases because you didn't do something correct, right? You could actually damage the device. And it's important to know these limits. Okay. In summary, at a PN junction, the depletion region is formed. This depletion region is charged, but there are no mobile carriers. They're all immobile atoms there. This region has a built-in voltage due to charge space. The depletion width and the voltage depends on the doping concentration and temperature. The depletion width and the voltage depends on the doping concentration and temperature. You've seen that. The field is maximum at the junction. The depletion width increases with more reverse bias. This leads to a capacitance since depletion region charge depends on the voltage. Excess reverse voltage causes breakdown in junction. Right? Lightly doped junction is the avalanche breakdown, and heavily doped junction causes Zener breakdown. Right? So I hope you understood the basics of PN junction. You can go through the lecture notes again if there's any more points that you want to do. But more important thing is that if you can work out the equations, most of it is worked out, but if you can yourself work it out on a pen and paper, that will be very useful. And then understand what the equation says to you. That is even more important. Once you understand that, I think this chapter will become that much more easier, because this is the basic semiconductor device in a way, a junction diode, reverse bias junction diode is the most basic thing, and you will encounter that in multiple places. So if you understand this, you'll get a much better hang of what's happening in semiconductor.